Welcome to lesson 7.2. I really like this first example in this lesson because it's a really awesome application of vectors, of everything we've learned about vectors so far. Now, anytime we have an application or a story problem, we have to make sure we draw a really good picture. So let's start by drawing a picture. We have a plane that's going to leave an airport. So I'm going to call this right there my airport. Now, this plane leaves the airport with an airspeed of 175 miles per hour and a bearing of north 40 degrees east. So north, and then we go about 40 degrees east. So we know that is 40 degrees. And I'm going to call this vector A for airplane. So I could say the magnitude of this vector A is 175 miles per hour. Now, there's also a 35 mile per hour wind that is blowing at a bearing of south 60 degrees east. So we're going to do a little bearing here, south 60 degrees east. So about like that. And we know this is 60 degrees. And I'm going to call this vector W. So the for wind. Magnitude of vector W is 35 miles per hour. Now, we want to find the true speed of the plane and its true bearing. So the true speed and bearing of the plane will happen when we add these two vectors together. And we learned in the last lesson that adding vectors together is when we go from the start of the first vector to the end of the second vector. So this right there is my true vector. So I'm going to call that one vector T for true vector. And the true speed will be the magnitude of this vector. And then we also want the bearing of this vector. So it's going to be north and then some amount east. 40 plus whatever this little angle is will get us our true bearing. So let's start by finding our true speed. I want the magnitude of this vector. Well, there are a couple things I could fill in here. Number one, I could use my law of parallel lines, meaning that this line and this line are parallel. So the alternate interior angles of parallel lines will be the same. Basically saying if I have two parallel lines cut, then the angles that are alternating on the inside will be the same measurement. Meaning that this 40-degree angle will be the same as this 40-degree angle because they're alternating on the inside of those parallel lines. So I know that this is going to be 40 degrees, which means this whole thing is 100 degrees, 40 and 60. Now, here's why I really like this problem. I have a side, and an angle between them. This is side, angle, side. I can use the law of cosines to solve for this side. So if I want to solve for this side, that's T. That side squared is going to equal the other two sides squared added together. That's law of cosines, minus 2 times those two sides again, cosine of the angle across, which is my 100-degree angle. So let's plug in all this stuff. I'm still solving for the magnitude of t, but I know this is 175. I know this is 35. And to solve for t, all I have to do is square root both sides to get t by itself. And I can plug all that into my calculator to get that the magnitude of t is 184.329. However, instructions say rounded, right here, rounded to the nearest mile per hour. So my true speed is 184 miles per hour. So basically we started at 175 miles per hour and the wind is helping us go a little bit faster. So there's my true speed, the magnitude of the vectors added together. Now the last thing I need is the true bearing, which means I need this angle, because I can do 40 degrees plus that little angle, and that will give me my true bearing to where the plane is actually headed, the direction the plane is actually headed. So if I need to find this angle, I now have a complete pair, which means I can now use the law of sines. So I can do sine of 100 degrees over 184.329. I'm using my accurate answer to make sure that my final answer is as accurate as possible. Equals sine of, let's call this the wind angle because it's across from the wind vector, over the wind side is 35. So this one, sine of 100 over this one equals sine of this one over 35. And let's just solve this with law of sines however you want to. I think it's easiest to just multiply both sides by 35. So you get sine of the angle across from wind equals 35 sine of 100 over 184.329. And take the inverse sine of both sides. We can type all of that into our calculator to get 10.777 degrees. So this little tiny angle right there is 10.777. So our true bearing looks like it would be north. Then I'd have 40 plus that 10.777 would give me 50.777. Rounded to the nearest degree would give me 51 degrees east. So that wind is pushing us a little bit off our initial vector. So that is a really awesome example of a vector application problem. We used vector addition, we used the law of sines and the law of cosines from chapter 5, a really great review. We talked about alternate interior angles, which is a good geometry review. Basically, this is just a really awesome review kind of problem. Anyway, now that we're done with that, in the next video, we'll actually move on to the new stuff for today's lesson, talking about unit vectors.